Have you ever wondered how many planets exist beyond our solar system, in the vast expanse of the universe? It's a question that has captivated humanity for millennia and continues to drive our exploration and understanding of the cosmos. Recently, a new solar system has been discovered, boasting 6 confirmed exoplanets and a possible 7th. This discovery is like finding a new puzzle piece in the grand cosmic jigsaw, providing us with vital clues about the formation and evolution of planets. The team spearheading this research is led by the University of California, Irvine. They are like cosmic detectives, using a variety of observatories and instruments to measure the exoplanet's masses, orbital properties, and atmospheric characteristics with unprecedented precision. Their findings are reshaping our understanding of the universe, one exoplanet at a time. Our understanding of the universe is expanding thanks to these researchers' tireless efforts. The researchers have done a remarkable job in gathering the most precise measurements of the exoplanet's masses, orbital properties, and atmospheric characteristics. Our journey takes us to the TESS-Keck Survey, a global collaboration that has brought to light the most detailed descriptions of exoplanets orbiting TOI-1136, a dwarf star in the Milky Way galaxy, over 270 light-years away from Earth. This survey is an extension of the team's initial observation of the star and its exoplanets in 2019, using data from the Transiting Exoplanet Survey satellite. This initial project provided a glimpse into the world of these celestial bodies, offering the first estimate of the exoplanet's masses. This was achieved by clocking transit timing variations, a measure of the gravitational pull that orbiting planets exert on one another. A sort of cosmic dance where the rhythm and pace tell us about each dancer's weight and speed. But the team didn't stop there. They went further, combining this data with a radial velocity analysis of the star. With the help of the automated Planet Finder telescope at the Lick Observatory on California's Mount Hamilton and the high-resolution Echelle spectrometer at the Keck Observatory on Hawaii's Mauna Kea, they detected slight variations in stellar motion using the Doppler effect. This technique, akin to how a siren's pitch changes as it moves towards or away from us, helped them determine planetary mass readings with unprecedented precision. To achieve such exact information, the team built intricate computer models using hundreds of radial velocity measurements layered over the transit timing variation data. It was a painstaking process, riddled with trial and error, but the results were well worth the effort. The team had developed one of the most complicated planetary system models in exoplanet literature to date. The richness of detail uncovered by this study has been extraordinary. The intricate dance of these exoplanets around their star, their masses, their orbits, and their atmospheres has been revealed in vivid detail, enhancing our understanding of these distant worlds. These findings have opened a new chapter in our understanding of planet formation and evolution. Determining the planetary mass readings was no easy task. A team led by researchers at the University of California, Irvine, took on this complex process with gusto. They embarked on the journey of combining 2 types of readings: transit timing variations, or TTV data, and radial velocity analysis. This approach was not only innovative, but also proved to be immensely insightful. The TTV data was initially collected in 2019, providing the first estimate of the exoplanet's masses by clocking transit timing variations. This is essentially a measure of the gravitational pull that orbiting planets exert on one another. It's like a cosmic tug-of-war, with each planet subtly influencing the other's movements. Now, to add a layer of intricacy, the researchers also conducted a radial velocity analysis of the star, TOI-1136. The automated Planet Finder telescope at the Lick Observatory on California's Mount Hamilton and the high-resolution Echelle spectrometer at the Keck Observatory on Hawaii's Mauna Kea were instrumental in this part of the process. These high-tech tools allowed the researchers to detect slight variations in stellar motion. It's a bit like watching a pendulum swing, but instead of a simple back and forth, the star's motion is influenced by the gravitational forces of its orbiting planets. The changes in motion were detected through the red shift and blue shift of the Doppler effect, a phenomenon that affects the light we see from moving objects. The team then constructed computer models using hundreds of radial velocity measurements layered over TTV data. This combination of readings not only provided a more comprehensive understanding of the system, but also allowed for unprecedented precision. The process was challenging, requiring trial and error. But the result, as lead author Corey Beard, a UCI PhD candidate in physics, so aptly put it, we were really happy with our results after developing one of the most complicated planetary system models in exoplanet literature to date. This meticulous process has led to unprecedented precision in planetary mass readings, a testament to the power of innovation, determination, and the relentless pursuit of knowledge in the vast expanse of the cosmos. To understand the planets in this solar system, the team had to create complex computer models. This is not a task for the faint-hearted. It involves a deep dive into the world of radial velocity measurements and transit timing variations, or TTV data. Imagine trying to understand the subtle dance of planets around their star, the gravitational tugs they exert on each other, and how this dance alters the light we see from the star. The team started with hundreds of radial velocity measurements. These are readings of the slight back and forth motion of the star caused by the gravitational pull of its orbiting planets. To observe this, they used two powerful tools: the automated Planet Finder telescope at the Lick Observatory on California's Mount Hamilton, and the high-resolution Echelle spectrometer at the TESS-Keck Observatory on Hawaii's Mauna Kea. The star's motion, seen in the redshift and blueshift of the Doppler effect, gave the team crucial clues to the masses of the planets. But the radial velocity measurements were just one piece of the puzzle. They also had to consider TTV data, which offered the first estimates of the exoplanets' masses by recording the variations in their transit times. As the planets orbit their star, their gravitational pulls on each other cause slight changes in their orbital periods. By carefully studying these variations, the team could infer the planets' masses. Combining these two types of readings in computer models was a challenge. It took a lot of trial and error, a lot of fine-tuning and tweaking. But as lead author Corey Beard, a UCI PhD candidate in physics, said, the results were worth the effort. The team developed one of the most complicated planetary system models in exoplanet literature to date, offering unprecedented precision in planetary mass readings. This intricate dance of data and modeling, of trial and error, has led to a deeper understanding of this intriguing solar system. The knowledge gained from these models is more than ever before. The mysteries of the universe are gradually being unraveled, one exoplanet at a time. The study of these exoplanets has significant implications for our understanding of the universe. The sheer number of planets in the TOI-1136 system has sparked an increased interest in further research. It's not every day you come across a solar system with 6 confirmed exoplanets, and possibly a 7th. That's like finding a needle in a cosmic haystack. These multiple exoplanets present a unique opportunity for astronomers. When you have several planets in the same system, you can control for variables that depend on the host star. This allows us to focus on the individual physical mechanisms that give each planet its unique properties. It's a little like studying siblings in a family. You can learn a lot by looking at their similarities and differences. But what makes this system even more intriguing is its relative youth. TOI-1136, the star at the center of this system, is only about 700 million years old. Now, I know that might sound ancient to us, but in stellar terms, it's barely out of the nursery. Studying such a young star and its planets is both a challenge and a fantastic opportunity. Young stars are active, with more magnetism, sunspots, and solar flares. This intense activity affects the planets in its system, shaping their atmospheres and possibly even their evolution. It's like being able to watch a time-lapse video of a planet's life, from its turbulent youth to its more placid adulthood. So, what does all this mean for us? Well, each new piece of information we gather from systems like TOI-1136 helps us to build a more accurate picture of the universe. It's like we're detectives, piecing together a cosmic jigsaw puzzle. The more pieces we find, the clearer the picture becomes. This research brings us one step closer to understanding the mysteries of our vast universe.